How you doing, Eric?
Good evening. Am I the first one in or the only one in?
You're the first and only one so far, but we're about 6 minutes early, so it's all good. You have a good weekend, Eric?
I just flew in
Okay,
yesterday and then I had a full day of work.
that's tight. Where'd you have to go over the weekend?
Well, it was all last week. I was at a conference for work
Oh
and
yeah, that's
meeting.
right.
Yeah.
I think you had mentioned that to me. Well, that's cool. Not so easy to recover after a conference and then flying in and then going to class or work and then class. Hey
Yeah.
Jerry, hi Lauren. Anybody have any questions while we're
Hi.
waiting for everybody else to come in?
I was wondering for the like substitute test. I
Mhm.
didn't see that. Do you know when
That's
it's
not up
gonna
yet.
be?
For the
Okay.
midterm.
Yeah.
Yeah, that'll be up either I suspect tomorrow, but it'll be either up tomorrow or it'll be up Wednesday. And like I said,
And
you're
you
gonna have at
said
least till Wednesday of next week to turn it in.
okay, perfect. Awesome. Thank you.
No problem. Hopefully everybody's started taking the practice test for the next test, which covers the next. I think I ended up doing 3 chapters instead of just the normal 2 that I normally do. So I made the due date on that Wednesday. I really just didn't want to have 2 tests hanging over you or have to have you remember 2 tests over the Thanksgiving break. So I made it due Wednesday. If you have a problem and you just can't get it done, just let me know and I can extend it through the break. I don't mind that. It's just like I said, I didn't like the thought of you guys thinking, oh crap, I got a Thanksgiving break and I have 2 tests due. Hello, Jamie. Still got about 3 minutes. So you're welcome to ask questions if you want or just hang out. Actually, I know one thing I'm going to do. I have a little bit of an extra credit assignment that would be good for you guys to do. So I'm going to go ahead and write it up a little bit here. Another person coming in. Yeah, we're coming in. right. All right, well, it's 5:20, so I guess we should go ahead and get started. Again, I asked, does anyone have any questions for us before we get jumping into the new material? I did send out an email. Hopefully you all got the, saw that the new practice test is up. Both new practice tests. We had one for the midterm, which was already put up, but I also made a new one for the next test. And your next test is supposed to be due by 11:59 p.m. Wednesday. I was just telling some other students, if that's really too quick, like you got something big going on, let me know. I can extend it for you. I just didn't like the idea of having 2 tests due over Thanksgiving break. But like I said, if you'd rather do that, then I'm okay with it. But like I said, you're going to have till Wednesday of next week to turn in or to make sure you complete all your attempts on the midterm. Actually, I think I just gave you one. Yeah, I gave you one attempt on the midterm, but this one's due for just the test of the next, I think I made 3 chapters. That one's due Wednesday at 11:59 p.m., which is 2 days from today. So any questions?
Professor, I have a question.
Yes.
So for the homework that's due tomorrow, I
Uh-huh.
was wondering if maybe we could get an extension on that just so I can use that time to study for the test that's due on Wednesday.
What chapter is the one due tomorrow? Do you recall?
I think it's 36, but I
Yeah,
can't
I think-
remember.
Yeah, I'd actually planned on pushing the relativity back till Monday anyway, so we'll do that.
Okay, thank you.
No problem. Anyone else? All right, so I have a little extra credit assignment that I'd like you guys to consider, because this is actually the perfect time for you to see it, and it's also the perfect time for you to learn something about physics and engineering in general. Let me go ahead and share my screen. So it turns out that in reality, the physicist rarely gets to solve a solution, a problem exactly. In other words, most things are approximations, or basically we've done numerical techniques to approximate the solution, whether it be solving a differential equation or whatever. And one of the things that often requires is like a Taylor series, or in this case, as you see up here, that's called a Maclaurin series. The only difference being a Taylor series would have an A, and everywhere you see the little 0, and it'd be f, the ith derivative of f evaluated at x equal a times x minus a to the ith power times 1 over I factorial. Okay, so that's your typical like Maclaurin series or Taylor series, except for the special case of a equals 0. And I've given you that formula. So what that means is, for starters, the 0 factorial is defined to be 1. 1 factorial is defined to be 1, and n factorial, in case y'all didn't recall, is n times n minus 1 times n minus 2 ... on up to 2 times 1, so on and so forth. Oh, I should probably make that a little clearer there. Hold on. Times 3 times 2 times 1. Okay, so that's what factorial means in general. We're just trying to, oh, I didn't realize I had that much space between that and the edge of the paper. Didn't have to make those numbers so small. But anyways, so that's what the factorials mean. And like I said, those I, that power in the parentheses on the F, is really a derivative. So the 0th derivative is just the function. The first derivative is, of course, the first derivative, and the 2 up there is the second derivative, the third derivative, and so on and so forth. What I'm asking you to do is apply that formula for f of x equals sine x, and then apply that formula for f of x equal cosine x, and then apply that formula for f of x equal ex, e to the x, which I think you'll find is quite easy, because you can imagine the e to the x derivative is just e to the x, and the second derivative is just e to the x, and third derivative is just e to the x. And then once you have that e to the x, I'd like you to fill in what happens when you do I x instead of x, where I is the square root of -1. So again, I'll put in, well, it's unfortunate that I used I up there because that could lead to confusion. Let's quickly change that just to make it a little less confusing. So what I'm going to do is I'm going to change this to, whoa, did not mean to do that. I'm going to change this to L. Yeah, that's that word, L. And then I'll change this to L. Whoa, no. And I'll change this to L. And I'll change this to L. Okay. And that I did that just because I'm getting ready to write that I is the square root of -1. Okay, so that's what I mean down there is I is the square root of -1. I will tell you, you're basically going to get x minus x to the third over 3 factorial plus x to the 5th over 5 factorial minus ... This one you're going to get basically 1 minus x squared over 2 factorial plus x cubed, or excuse me, x to the 4th over 4 factorial minus ... And you can imagine what e to the x is going to be. It's basically going to be all those 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed plus ... So it'll be something like that. I'm going off the top of my head, so there's some probability that I made a mistake, but I will put in an extra slot for you to turn this in. This is a very good extra credit, and we're going to make use of it immediately today in several ways. So I just wanted to give you this as an extra credit. And it hopefully will bring back what you did in calculus and let you see that it actually is something that's useful, and specifically let you see a little bit of the reality of physics and engineering is that we can't find nice, easy solutions. You know, y equals sine of omega x or something like that. We can't always find that for things. We often have to approximate them with stuff like this. So anyways, that's something you should do. What we're studying today is in fact oscillations. So this is chapter 14. Oscillations. Okay, so to do that, I'm going to first introduce you to Hooke's law. Let's remember Hooke is the nemesis, one of the many nemesis of Isaac Newton. He was the guy that was the president of the Royal Society just before Isaac Newton, and he often bickered with Isaac Newton and tried to claim discovery of things that Isaac Newton had discovered. So Isaac Newton didn't care for him that much. And I even told you the story about how he said, if I have seen further than others, only because I stood on the shoulders of giants. That was in the presence of Hooke, who had a bit of a short man's complex. So he basically was saying, if I have seen further than others, only because I stood on the shoulders of giants, not hobbits like you, Mr. Hooke. So that's kind of relationship that they had. He actually claimed to have figured out that the orbits of the planets were conic sections and all this stuff by 1/r² law. However, when people asked him to do the work and show it to him, he never provided it. Newton, however, did do that and did provide it. So just an ongoing thing like that. But one of the things he did is he discovered that basically if you apply a force to, let's say, a long steel rod, if you try to compress it, let's say you stick the long steel rod, you stand it up vertically, and you stick it on something really hard like concrete or the deck of a ship, and you start pushing down on the top of it. As you push down on the top of it, what's going to happen is it's going to compress the rod, and the amount of compression will be given by force equals negative K times X, where K is a constant that's based on the material. We often use it with springs, and that's mainly because springs behave the same way. But we can actually see the movement with very small forces, where if I actually took a steel rod, I'd have to put on the order of tons on it to see it move even millimeters. So that's why we do that. Now, you might wonder what's the negative about. Well, what that means is if I assume that the end of the rod was at X equals 0, then if I compress the rod in the negative direction, the force would actually push in the positive direction. So putting in a negative X in there would actually make a positive F, and that's exactly what we expect. Now, if you want to talk about what force you had to apply to it, now that would be F equals KX. So we will, on occasion, drop the negative to just find a magnitude. But anyways, we've already studied this before. We even know that the potential energy of that is 1/2 kx squared. We did that by integrating the integral of f dot dx, and the integral of f dx becomes the integral of kx dx. That's 1/2 kx squared. So the potential energy for the spring is 1/2 kx squared. So we already knew that. Now, let's imagine that we have a spring, say, and it's set up tied to a wall right near the bottom corner of the wall. So the spring comes out, and it's attached to a mat. What's that?
Would you be negative 1/2, or would it just be 1/2 like you said?
Yes. So when you're calculating that, when we integrated it, it actually comes out the positive, because what we're calculating is the work done on the spring. So that's the external force, or I guess that probably external force might be the best way to think of it, that's being applied to it. So in that case, it's positive kx. But yeah, you're right. If I just took that formula and did the integral of f dx, you obviously get a negative. But I didn't take that formula. I took the formula F external is equal to K times X and did that. And you see that since I didn't put a range, I'd have to put a constant of integration there. Okay. In general, you go from x1 to x2 or x0 to x1 or whatever. So what I'm going to do now is I'm going to imagine my coordinate system as if it were like, let's say right here. And let's say that's the x-axis. Now, if I were to move the spring or move this mass so that the spring was here, then this distance right here is x, and you see that's a negative quantity. So that's the kind of problem we're talking about here. And you can see also that when you compress the spring that way, putting in a negative number for x, multiplying that by negative k would give you a positive f, and that should help you see what's going on here. So with that in mind, if this is a frictionless surface, then what we have is Newton's second law of motion, the summation of forces is equal to mass times acceleration, but I'm going to write acceleration as d2x over dt squared, which we know from dynamics. This is all in one dimension. So what I end up getting is negative kx is equal to m d2x over dt squared. What I'm going to do is rewrite this so that I get d2x over dt squared, and I'm going to divide through by k. I'll pull the x to the other side. That'll make it positive. And I will get, when I do that, I will get k, or excuse me, I'm going to divide through by m, not k, sorry, over m times x is equal to 0. Now, this is called the equation of motion. And that's the terminology we'll use in physics from here on out. So basically, whenever you set up a differential equation using Newton's second law, whether it be in F equals mx or F equals ma or F equals dp dt or F equals m d2x over dt or F equals m dv dt, they're all the equation of motion. A lot of times they're very simple and you don't have to solve a differential equation, but sometimes you do. And either way, they're called an equation of motion. In this case, it happens to be a second order linear. Now, linear means there's no x times x or x times dx dt or x times dx dt squared or anything like that. It's second order linear ordinary, meaning not partial derivatives, and homogeneous, differential equation. Okay. Ooh, I think it's okay. So basically, like I said, I explained the linear. The second order means the highest order of the derivative in the equation is the second. So obviously it's the second order. It's linear. I already explained that. It's ordinary because they're not partial derivatives, and it's homogeneous because when you put all the functions and variables that are related to the function. So for instance, this function x is a function of t. So if I put all the x's and t's on one side, then the other side will be 0. That makes it homogeneous. Okay. Now, if you've had differential equations, you'll see them solve it one way, and it's quite a bit different from the way your book does. And I'm going to sort of show that as well as show the way your book does it. But we're going to go ahead and solve this differential equation both ways and help you make some sense of how it looks in DiffEq versus how it looks in physics. So we've got the equation set up. Remember that form. It's the second order of derivative, in this case, x with respect to t, plus some constant times x, okay? Because anytime you see that differential equation, the solution that we get for this one will be a solution for that one as well, okay? So now I'm going to flip pages, and I'm going to write d2x over dt squared plus k over m times x is equal to 0. Now, in your differential equation class, they'll say let x of t equal a times e to the rho t, okay? Now, what you're looking for, and the reason why they choose this is, if you'll notice, the dx dt and the x are all like just being multiplied by numbers and then added together. In other words, they're not multiplied by functions or anything like that. So if you could find a function whose derivative or maybe even its second derivative repeats itself, then that might be a good candidate for an answer here. So if you take the derivative of something that repeats itself, like derivative of e to the rho t is going to be rho e to the rho t, then you get a e to the rho t in both terms. And obviously that would be exactly the kind of solution you want. So that's why you think of using that one. We do it a little differently in physics, but I'm going to play this out and let you see why. So now what I'll do is I'll say, well, x dx over dt is going to be, of course, rho times a e to the rho t. And then d2x over dt squared is going to be rho squared a e to the rho t. So if we plug this back in, what we can see is we get rho squared a e to the rho t plus k over m a e to the rho t is equal to 0. But we notice that, for instance, this right here is just x of t, as is this. So we can write rho squared plus k over m times x of t is equal to 0. But this is true for all t. That means, for starters, x of t equals 0 is not very helpful, right? If it was just purely x of t equals 0, that's not anything. That just means the spring's not moving. You never touched it, blah, 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 right? So that leaves us with the whole reason you learn factoring in algebra, namely, to solve an algebraic equation, you take a bunch of terms that are added together and you convert them to multiplication. And by converting them to multiplication, you have something times something times something times something equals 0. And the only way something times something times something times something equals 0 is if at least one of those factors is 0. So in this case, we're going to say, okay, well, rho squared plus k over m is equal to 0. That implies that rho is equal to the plus or minus I times the square root of k over m. So in your differential equations class, they would say, okay, well, this is a second order differential equation. So let me ask you something, everybody. We know that the derivative gives us what on a graph? What feature of a particular graph is discovered by taking the derivative of that function?
Max and minimum?
That too, yes. But there,
Parabola.
what's that?
Parabola.
Oh, yeah, for a parabola, yeah. But notice, remember, for instance, when we found a maxima, the way we did that is we set the derivative equal to 0, because on top of that, the slope is flat. And a slope being flat means the slope is 0. So what I was shooting for was that it's a slope. But y'all are all in the right ballpark. But I just had an open-ended question, I guess. Now, what about an integral? What does an integral find on a graph?
The area under the curve.
Yeah, the area under the curve. Now, this is the weird thing. Those two didn't have to be opposites, but they are. I mean, that's pretty amazing that they are. But the other thing is, because they're opposites, that means a derivative undoes a integral, or an integral undoes a derivative. Does that make sense to you guys? That's why they initially they call it an antiderivative. And that's sort of the fundamental theorem of calculus. So because of that, you can think, okay, well, this is a second order differential equation. So how many times am I going to have to integrate this to undo that second order derivative? Anyone? Twice, exactly. And if I don't have ranges of integration, what do you got to do with the integral? So you integrate just a function, but you don't have any range of integration. You don't have a. Yeah, you have to. I think I heard you right. Did you say you had add a constant?
I mean, I said undefined, which means you had a constant.
Oh, gotcha. Yeah. So, okay, sorry. Yeah. So, when you integrate a function without limits on the integral, then you say plus c. So, if you have to do that twice, then that suggests you're going to have two c's, right? Well, in math class, you look at this and you say, oh, I get two answers here. And in fact, they're what we call linearly independent. And whenever you have a full set of quote unquote linearly independent functions, you can represent any function at all with them. One such pair of independent functions, linearly independent functions, is e to the negative rho t and e to the positive rho t. In other words, you can't multiply e to the rho t by any number to get e to the negative rho t, unless it's another function, of course. So when they see that, they immediately would go, okay, well, we're now going to call x of t is equal to a1 e to the and I'm going to go ahead and write it out, negative I square root K over MT plus A2 e to the positive I square root K over MT. That's the way they do it. Now, if you're familiar with what I was showing you here, when we did this e to the negative x and e to the ix and e to the negative x, you would know that e to the ix is equal to cosine x plus I sine x. And e to the negative ix is cosine x minus I sine x. Okay, so you can see that parts of this A1E blah 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 plus A2E blah blah blah, parts of those are going to come together and might even get some cancellations depending on how A1 and A2 are defined. And not only that, you could possibly work out a way where that I completely disappears, or even if it didn't, you're going to ignore it anyways because it's imaginary, and we don't work in the imaginary world. Okay. So it turns out you can see that these e to the ix, e to the negative ix, they actually turn into sines and cosines. This is where we differ in terms of mathematics versus physics. In physics, we look at a mass on a spring and it's going wing, 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 wing. We think, wow, that really looks like a sine wave. So it's called a sinusoidal curve. And so here we go. In physics, we're going to say, let x of t equals some constant times cosine, and we could have used sine, by the way, but your author's choosing cosine, of omega t plus, remember it's two integration constants. One might actually, a constant might actually be found by the characteristic equation, which is what we just found when we found that rho was plus or minus I k times the square root of k over m. But we now have an a and a phi, and that gives us basically the equivalent of a1 and a2. It gives us the ability to choose two constants of integration, in other words. Okay, so when we do that, we see, all right, well, dx over dt, which is actually equal to v of t, just as a reminder, that dx over dt is the derivative of cosine with respect to time. The derivative of cosine is negative sine, and then the derivative of omega t plus phi with respect to time is omega. So I'm going to say negative omega a sine omega t plus phi, like that. And then that second derivative, d2x over dt squared, which is a of t, just again to remind you, that's going to be negative omega squared a cosine omega t plus phi. Now you're probably wondering what the poop is omega, and maybe even what the poop is phi. Well, if you think about the sine function and cosine function, when you first learn about them, you often learn about them with degrees, but later you learn about them with radians. So if you just picture this, omega is something that has units of radians per second. And in fact, omega is equal to 2 pi times the frequency. And in fact, frequency is 1 over the period, or vice versa, period is 1 over the frequency. Okay. Now the phi is called the phase angle. And it just gives us room to make particular choices, which you'll see in a second. Okay. So now if I plug this back into my equation, what I get is the equation of motion becomes negative omega squared times x of t plus k over m times x of t is equal to 0. Remember, I did the second derivative. There was no first order derivative, but you can see this part right here. that's just x of t. So this is negative omega squared x of t and plus k over m x of t. So I get a characteristic equation again, just like you learn in your differential equations class. Okay, that's going to be negative omega squared plus k over m times x of t is equal to 0. And that gives us, in fact, that omega is equal to the square root of k over m, which is the same thing we found earlier, and that's good. And in fact, you could say plus or minus. Now, it turns out by using cosine, the plus or minus doesn't matter because cosine is an even function. So you can sort of think of that as why we ignore that. So now we can say x of t is equal to a cosine times square root k over m times t plus phi. All right, so now we have that. Does anybody have any questions about what we did there? Okay. So basically, we took the equation of motion for any mass on a spring, really. That's why I kept everything in terms of symbols. So let me show you a couple example problems to make this sit right. First off, we're going to attack Hooke's law. So imagine, whoa. Let's imagine a,
Professor,
yes,
can you go back to the previous screen for a moment?
yes. I keep shrinking my screen and not using the whole page and not even noticing it.
Okay, thank you.
No problem. So imagine a car of mass 1,224 kilograms that after 4 people sit in it, it lowers by, let's say, 3.00 centimeters. The mass of the 4 people is going to be 204 kilograms. Okay. What I want to know is A, what is the spring constant for the car's spring / shock setup. And then B, what, or no, let's do scratch that. How much would the car lower if M4 equaled 306 kilograms? So there's our problem. Okay. Now here we're just talking about magnitudes. I don't need to think about the negatives and all that stuff. Obviously, if you push down on a car, the force of the spring is going to push up. That's why there's a negative sign in there. But we're really just talking about the magnitudes. So what we're going to use is F equals KX. Now, when the people sit in the car, their force is not 204 kilograms. Their force is what? Anybody know? How do we get a force from 204 kilograms?
1,999.2 newtons.
Yes. You multiply by 9.80 meters per second because that's weight is equal to mg. That's equal to K times 0.0300 meters. And notice to 3 sig figs, that's essentially 2,000 newtons. So K is going to be 2,000 newtons with carrying 1 extra sig fig divided by 0.0300 meters. And that gives me a spring constant of, y'all can check me on this. $6.667 times 10 to the 4th newtons per meter. So that is the typical units for a spring constant. It's a certain number of newtons per meter, and that's in the standard SI thing unit. So that makes sense. So we now have part A answered. Now part B, can anybody tell me off the top of their head when M4 goes to 306 kilograms, what does X go to? Anybody take a guess on that one? How much bigger is 306 than 204? It's 1.5 times bigger. So anybody want to take a guess how much X is going to be for this part?
$459.
Yep, 4.5 basically. So notice that weight for part B is equal to 1.5 times weight for part A. Whoa. Which implies X for 4B should be equal to 1.5 times X for 4A. So if we actually work it out, what we'll see is X is actually equal to F over K. And of course, in this case, that's 306 kilograms times 9.80 meters per second every second divided by 6.667 times 10 to the 4th newtons per meter. And lo and behold, that gives you 0.045. Yep. Yeah, 449, which is essentially 4.5. So does that make sense, everybody? All right.
Yep.
I'm going to move on to the next page, and we're actually going to use this example again. So now let's imagine for a second that that same car is riding down the road, and it's got kind of crappy shocks and shock absorbers and all that good stuff. And it's got the original 204 pounds of people in there, or 204 kilograms of people in there. So in fact, we're going to have 1,428 kilograms is the total mass of the car. And what we want to find out is what is the angular frequency of its oscillation? Because if the springs are kind of crappy, it will bounce sort of like Uncle Buck's car did. If you ever saw the movie Uncle Buck, if you haven't, yeah, I demand y'all watch it at some point. There's a lot of 80s movies that you're going to have to 80s and 90s movies that you're just going to have to watch. They're just too good not to watch. And that's 16 Candles, Breakfast Club, Pretty in Pink, and maybe some man movies, but Uncle Buck's another one. And probably Home Alone's another one. So anyways, let's take the same car. Now the car has a mass, M equals 1428 kilograms. And we found that K was equal to 6.667 times 10 to the fourth newtons per meter. And we want to know what is omega, and then what is the period, and what is the frequency. Omega is a little too abstract, so I don't like just calculating that. So I generally try to get you to think about frequency. And we'll talk a little bit about what these things mean. Now, what we know is, here's our solution. What we know is omega is equal to the square root of K over M. So that's the square root of K, which would be 6.667 times 10 to the fourth newtons per meter divided by 1,428 kilograms. If you look at that, you can see a kilogram is a newton is a kilogram meter per second squared. So when you divide the kilogram meter per second squared by a meter, you get a kilogram per second squared. And that kilogram cancels out with the kilogram below. So you just get a per second squared, which means you have no units divided by second squared under square root. And in fact, the units are going to come out in radians per second. So if I do this multiplication or this problem, I'll do the square root of 6.667, e to the fourth divided by 1428, close parentheses, and I get 6.83. 6.833, carrying one extra sig fig, radians per second. Again, that's not very useful. That's not very a figure that you're used to seeing very much of. So what I want to do is put it in a more reasonable context of something that y'all might be more familiar with. So what we're imagining here is a car riding down the road. Maybe there's a magic marker spot on the bottom of their bumper. That magic marker spot is going to be doing like this. Okay. And in fact, we know from the sine wave that from here to here is like one wavelength, if you will. Okay. And in fact, the time taken is equal to one period. Okay. So when I figure out period, what I'm saying is that's how long it'll take to go from the equilibrium position to the high to the negative position. Oops, I did it too long. Sorry about that. I just realized. Oh, good. It's got multiple colors now. Isn't that nice? Okay. Okay. That is the distance. Sorry about that. So, and I'm putting that lambda up there, not because the lambda makes any sense, but just because you know that's what the wavelength of the sine wave is. So that's one period, or that's one cycle. So when I find the period, that's how long it takes to go from equilibrium position through its highest point, through equilibrium position, through its lowest point, and then back to equilibrium position. So now let's say omega is equal to 2 pi f, implies f is equal to omega over 2 pi. So F is going to equal 6.833 divided by 2 pi. Which gives me about 1.087. Now, to make sense of this, you can call it cycles per second, which is also the same thing as 1.087, again, carrying one extra sig fig, hertz. Okay, so this time is related to this period by t is equal to 1 over f. So if I take that and say raise it to the -1 power, then I get 0.9196 seconds. And you can call that seconds per cycle, which is exactly what it means, but either way is acceptable. So we now know that the frequency is that and the period is that. So that means it'll take about 92 hundredths of a second for it to go from equilibrium through the highest point, through the lowest point, and then back to equilibrium. That's going to take about 0.9196 seconds, or about 0.92 seconds. Make sense? All right. So now what I want to do is show you how you're supposed to use the differential equation result. So what we did is we found that when you had d2x over dt squared plus k over mx is equal to 0, that gave us x of t is equal to a times cosine square root k over m t plus phi. Now, I told you needed basically two constants of integration to integrate twice. Well, that means this type of equation, a second order differential equation, needs two initial conditions. So, and that's always true. If you're a third order differential equation, you're going to need three initial conditions. If it's fourth order, you're going to need four. It needs two initial conditions. In some sense, they're often called boundary conditions, but that's definitely when you're talking about things in space or whatever. So often what people will give you is x0 is equal to x at t equals 0. And they might say v0 is equal to dx over dt evaluated at t equals 0. That's the normal scenario. They don't have to do that, though. They could give you two x values. They could give you x at t equals 0 and x at 1 second, and that would be sufficient. Or they could give you x at 1 second and x at 4 seconds, and that would be sufficient. Or they could give you v at 0 seconds and v at 1 second. All that kind of stuff is fair, just as long as they're independent. So if you were actually given the scenario where I literally just used that, so we're pretending like we have x0 and we're pretending like we have v0, then what this means is x0 is equal to a times the cosine of phi, because I actually evaluated t equals 0, that means omega t is going to be 0. So this would actually allow you to figure out cosine, or excuse me, allow you to figure out phi in terms of a. Now, if you also had, using the other condition, you'd say v0 is equal to negative omega a. Remember when we took the derivative, we got negative omega a times the sine. Again, the omega t is going to be 0. So in this case, it's phi. So what you could do is you can actually divide v0 over x0. And what you're going to get is negative omega a sine phi over a cosine phi. That cancels our a's out, which is nice because we didn't want to deal with them right yet. And that, in fact, gives us that. That gives us that tangent phi is equal to it's going to equal negative v0 over omega x0, or phi is equal to the tangent inverse of negative v0 over omega x0. So this works every time. You can literally just plug that in every time if they gave you v at t equals 0 and x at t equals 0. They're not always going to do that though, so just be careful. But that's one way. And now that we have phi, we can actually picture a triangle with that phi. And of course, the tangent being that means this side should be omega x0, and this side should be negative v0. And of course, that means this part right here is v0 squared plus omega squared x0 squared. So you can say cosine, or you can say A is going to be equal to x0 over cosine phi. Cosine phi would be adjacent, which is omega x0 over hypotenuse, which is the square root of v0 squared plus omega squared x0 squared. So that's another way we could actually find what A is. Notice in this case, the x0s here cancel out. So we just get the square root of v0 squared plus omega squared x0 squared over omega, and that's A. Again, this works for every one of these, assuming that they give you the x at t equals 0 and the v at t equals 0. Okay, if they don't, then they can't use it. I don't recommend you using formulas like that. I recommend you just going through this process. Any questions on that? Because I'm getting ready to show you an example. All right, let's get out of the mathematical world and go to a real world problem. So let's imagine that we take a spring and we hang it at equilibrium, and then we hang a mass of 2.04 kilograms from it, and it stretches an amount x is equal to 30.0 centimeters. Now that has to be a very special spring. Remember, if you actually stretch a spring too far, you've probably all had slinkies before, and if you stretch them too far, it'll actually spring it and make it not behave like it's supposed to. It'll never go back to normal. So you got to be careful with that kind of stuff. But we're just assuming that this works for this scenario. Okay. So the first thing I want to do is figure out what is K. And then I'm going to take that same spring and that same mass and set them up on a frictionless surface. And do something with it. Okay. So for starters, solution. And now right now I'm just trying to find K. Okay. So K we know is going to be F over X. This was hanging, so it had to be 2.04 kilograms times 9.80 meters per second every second divided by 0.300 meters. So when I do that math, I get 2.04 times 9.8. That gives me 19.992 newtons divided by 0.3. Oops. That gives me 66.64. Newtons per meter. Notice I carried one extra sig fig again. Anybody second me on that? All right. So now what I'm going to do is I'm going to say this is my coordinate origin at the equilibrium position. And this is X. Okay. And what I'm going to do is I'm going to push the spring, the mass, such that it's way over here. And in fact, this distance right here would be a negative, let's say 0.200 meters. Okay. And then I'm going to release it. Okay. So when I do that, what that tells me is that x of 0 is going to be negative 0.200 meters. And that tells me that v of 0 is equal to 0. Does everybody see how that works out that way? And we already know that x of t is going to be a times cosine square root k over m t plus phi. So again, our solution will be what we're trying to find I want to know what is A, what is phi, and what is, of course, x of t. In other words, write out the whole function. I want to know B, V max equals question mark. C, I want to know A max equals question mark. And D, I want to know V of 2.00. No, let's not do that. Let's do something smaller. I want to do V of 0.31 seconds equals question mark. Okay. So I can take 1, 2, and 3. I can combine 1, 2, and 3. First off, let's do 1 and 3. 1 and 3 gives me that negative 0.200 meters is equal to A times the cosine of phi. Now, you might be compelled to guess that phi equals 0, but we don't know that. So if we did know that, then we could solve for A. But that means I just need to try 2 and 3. So 2 and 3, remember, we've already taken the derivative, so we know what the velocity is. In this case, what we're saying is 0 is equal to negative omega A sine of phi. Again, the omega t is equal to 0, so that's why I just got the sine of phi. Now, this case is really good because the only way that can be 0 is either omega 0, that makes no sense, A is 0, that's a useless problem, and or sine of phi is equal to 0. And if you remember what the graph of sine x looks like, the x has to be 0 or pi or 2 pi or something like that. Obviously, the smarter choice would be take the 0. So this implies phi is equal to 0. Boom, that helps. And now when I plug this back into this equation, I get negative 0.200 meters is equal to k times the cosine of 0. And the cosine of 0 equals 1. So that tells us A is actually equal to negative 0.200 meters. And actually, this gives us the superhero treatment. Okay, so now I've gotten A and phi, and now I can say, of course, that x of t is actually equal to negative 0.200 meters times cosine of the square root of k over m. Let's go ahead and compute that. Actually, I did that earlier. No, I didn't. The square root of K over M is the 66.64 divided by 1428. No, this was something different. The 66.64. I'm going to divide that by the mass, which in this case is 2.04. And then I'm going to take the square root of that. And I get 5.714. So this is 5.7, actually 715. And that's radians per second times T. I'm just going to leave that unit off though. And remember the phi is 0. So that's what my x of t is. So this is what I mean by, yeah, don't use those formulas. It's better to just plug the values in and see if you can find out what a and phi are. Any questions on that? Now, if you look and you understand how sine works, when you take the sine or cosine, let me go ahead and draw a graph of cosine too. Graph of cosine looks like this. And you see that both of them go back and forth between -1 and +1. Right? So anything you multiply by sine or cosine is going to be the biggest. That's going to be the amplitude. So we know that the velocity is omega a times the sine of blah, blah, blah. So obviously for part B, the Vmax is equal to omega, I'm going to say magnitude, is equal to omega times the magnitude of A, because really don't need the negatives there. So what I'm going to do is I'm going to say the omega, which is this, times A, which is 0.2. And that gives me 1.143. Meters per second. Remember, the omega is radians per second, but radians is like meters divided by meters, so it's not a true unit. So you can just drop them and add them as needed. So now I got the Vmax is 1.143. The A max, if you remembered when we actually did the second derivative, you'd realize that the A max is just omega squared times A. So for part C, A max is just going to be omega squared times the magnitude of A. So in this case, I'm going to say 5.715476. I used a bunch of digits. Squared times 0.2. And this gives me 6.533. Meters per second every second. Any questions on that? Now, I'd really like to know the period and that sort of stuff too. I figured out the omega, so I might as well do that. So I'm going to go to the next page. Anybody need this before I move to the next page? Okay, so omega, yes, did you need it, Jamie?
No.
Okay. So we found omega was 6 point, where did we find that anyways? Oh, 5.6, no, it wasn't that. It was 5.715. So omega was 5.715 radians per second. Okay, now that's useful for us because omega is equal to 2 pi f. So f is equal to omega over 2 pi. and I can get a frequency to make some sense out of what's happening here. So I'm going to take this 5.714547, say, for 8. And I'm going to divide that by parentheses 2 times 3.14159, close parentheses. And that's going to give me 0.909. 909, and the next digit is actually, well, I have to take 249 hertz. Okay, so both of those are that. So what that tells you is the number of cycles per second is 0.909. So it takes a little bit more than 9/10 of a second to complete one cycle. The more important thing for me is the period. The period is 1 over the frequency. So I'm going to raise that to the -1 power, and that's going to give me the period is 1.099. And then 5 seconds. Oh, so I probably misstated something when I was wording it, because I'm noticing now that the wording's funny. But the F means that 0.909 cycles happen every second. So that's it's not 90% of a second, it's 90% of a cycle passes by in 1 second. So that means in order for you to have a whole cycle, you have to go more than 1 second, which is obviously from this 1.90995, or technically we'd have to call that 1.10 if we rounded it to the appropriate place. The reason why I say that is because I want to know Vmax equal, or excuse me, not Vmax. I want to know V of 0.31 seconds, which is negative. Now, omega times A, we've already found that Vmax, and that Vmax was 1.143. And actually, the omega times the negative A would make this positive, so I should put it that way. And that's meters per second times the sine of 5.715 radians per second times 0.31 seconds, like that. So now notice that's coming out in radians, so I technically have to put it in radians, but what I'm going to do is take those radians and turn them into degrees and then take the sine of that. So 5.715 times 0.31, that gives me a certain number of radians. Now I divide that by pi and multiply by 180. And that gives me 1.143 meters per second times the sine of 101.508 degrees. So I'm going to do sine of the answer. And this part right here, just for record's sake, I got 0.97990, like that, times 1.143. That gives me 1.120 meters per second. So we got an actual positive velocity. That's, well, so that's V of 0.31 seconds. That's the answer we're getting. Now, why did I do all that? Well, what I wanted you to see is I'm going to take a graph here, and I'm going to make this a graph of X versus T. I also want to make it a graph of V versus T. And I also want to make it a graph of A versus T. And I'm going to do it all in this nice little order. Oops, erase stuff again. So what I'm going to do is lay out the times in a reasonable amount. I'm going to say that's half a period. That's a whole period. This is 3/4 of a period. And this is 1/4 of a period. So we're all lined up together is the main thing I'm shooting for here. So when I look at my X, it was negative 0.20 times the cosine of omega t. Okay. So it's a negative cosine. And in fact, it is negative 0.20. So what I'll write down here is negative 0.2. This will be measured in meters. And what I get is this graph will look like this. Like that. And that's positive 0.20 meters. Now, that's X of t equals negative 0.200 meters times cosine of, again, omega t. Now, the omega t we found was 5.715, and we found the time was 1.09 seconds. So this is 1.0995 seconds. And of course, if we did 1.0995 divided by 2, this would be 0.54975 seconds. Okay. And this would be half of that. So that'd be 0.2749 seconds for this guy. Okay, why do I do all that? Well, we can look at the slope from t equals 0 all the way up to t equals 0.5497. Do you see that the slope is positive? It's 0 at t equals 0, which means its velocity is 0. But do you see that from there on out, the slope is positive? And what we predicted for our velocity at 0.31 seconds, which is noticed well under the 0.54, we saw that the velocity was positive 1.120. So that's exactly what we expected. That's one of the reasons I graphed this, is so we can make sense of whether that was a reasonable velocity at time 0.31. Now, our V of t, we figured out that that is in fact 1.143 meters per second times the sine of omega t. So in this case, we're going to have a regular sine curve, but it's going to wobble back and forth from 1.143 to negative 1.143. And this is in meters per second. So in this case, we're going to get sine there. Oops, went too low there. Like that. And then finally, A of t is going to be, did I calculate the A max? Yeah, I did. 0.533. Meters per second squared cosine. Now that one was negative, but the A was negative as well. So again, that gave us a positive. Same thing happened with this, the negative and the negative was positive. So this was negative. Yeah, I think that. So if we look at this, the slope is obviously positive for the first quarter period. So if we look at that, that means cosine, that would actually have a negative. So that's going to have to, no, it is a negative. Sorry about that. So in this case, it's going to be from 0.533, and this is measured in meters per second, down to negative 0.533. And it's going to be a negative cosine as well. So it's going to look like this, this, and this. Smoother, of course. So the main reason I want you to see this is look right here corresponds to this, and that's V equals 0. But that actually corresponds to A being 0 at that point too. Did I miss something here? I think I might have messed up when I graphed that A of t. The A of t, let me work this out on the side. We had x of t is equal to A cosine omega t. V of t was negative omega A cosine, or excuse me, sine omega t. And then, of course, the A was negative, so that gave us a negative times a negative was a positive. And then we said A of t was negative omega squared cosine omega t. Derivative cosine is negative sine, so that works right. And then we've got the A in there. That's going to be a negative, so that's definitely going to be a positive. Oh, yeah, that's what it is. Okay, gotcha. So let's regroup here. I got my signs off, so I can take this out, take this out, take that out. Okay. So, and I also need to take this out, that negative there. And now I'll put my red lines back in. Okay, so we see this is actually going to be a positive cosine. So with that in mind, we're going to start at the high point and go to 0. And then come to the low point and go back to 0. And then come back to the high point again. Okay, so what I was saying here is that V equals 0. We've got an acceleration that's still off phase. Anyways, I don't know what happened here, but I've got something off phase. But the main thing I was trying to show you, whether this, you might want to try this. Let me write this. Try these with Desmos or your graphing calculator. Okay, make sure you keep track of your signs. The A is going to be negative 0.2. The phi we found was 0, and graph these all on top of each other. And what I want you to see is that A equals A max when V equals 0, and V equals V max when A equals 0. That's the main thing I was trying to get you to see. Again, I'll say, don't trust. Now, the only other thing I want to show you today is it turns out if you also did a similar problem for a pendulum for a very small angle, this angle's theta, and this length is L, and this mass is M. What we see is there's a force, mg, acting on this. That can be broke up into a component, mg cosine theta, because this is theta as well, and then a component this way, which is mg sine theta. Okay. Now, the summation forces equals m d2x over dt squared gives us that m negative mg sine theta is equal to m d2x over dt squared. But if theta is small, and y'all know this because I just finished writing what the Maclaurin series expansion for sine theta was. If theta is small, then sine theta is approximately equal to just theta. And if you look at this, you could say this is an arc length S. This is a radius L. So S is equal to L times theta. And we're seeing S and X are about the same thing. So S is approximately equal to X. So then you could say, oh, okay, well, theta is equal to X over L. If I put that there, notice for starters, the M's cancel out. And I get negative G X over L is equal to d2x over dt squared. That gives me d2x over dt squared plus g over L times x equals 0. That's the exact same equation we had before. So I can immediately say, oh, well, that means omega is going to be the square root of g over L. And of course, omega is equal to 2 pi f. And of course, f is equal to 1 over t, and t is equal to 1 over f, so on and so forth. So we still have x of t is equal to a cosine omega t plus phi with that. So that's the main thing I want to show you, is yet another equation with the exact same form. And we didn't have to do anything because we see it's a second order derivative plus a constant times a zero derivative. So it obviously has the same solution with the same omega and everything. All right, time's up. You guys are free to go. I will wait for the last person to leave in case anybody has any questions. Remember, we do not have class on Wednesday. You guys have a good break and enjoy yourselves. And don't forget your 2 tests.
The second test is the final exam, right?
The midterm, the redo of the midterm, if you choose to do it.
Oh, we're redoing the midterm, and you split it up, right?
Yeah, that's gonna be posted probably tomorrow. It might even be posted tonight, and you will have until a week from Wednesday to get it done. I didn't even hear your baby interrupt, but thank you for apologizing. Anybody else have any questions?
You have some extra credit due on Sunday.
I did, or are you
That,
asking, do I?
Oh yeah, do you? Because I was looking on the what do you call it? The mastering physics, and I noticed there was like 4 extra homework assignments that are for extra credit. Is
Yeah.
that true?
Yeah, whenever you see them up there, if they're not chapters we covered and they're not chapters we're going to cover, then they're supposed to be extra credit. I try to mark them with an EC on it. So you might have seen one that I didn't mark with an EC. I'm not sure.
All right, thank you.
No problem.
I have a question for the chapter 36 homework.
Okay.
It says to calculate energy and momentum for relativistic particles and from relativistic equations to find relations between them. It gives me 2 formulas, and then it says find the momentum P in a laboratory reference frame of a proton going at a speed of 0.762 C. Use 938 MeV over C squared is the mass of the proton. And it gives me the formula P equals mv over square root of 1 minus V2 over C2.
Okay. So for starters, the momentum P is gamma times MP V. The kinetic energy is gamma minus 1 times M sub P C squared. I'm having a hard time making out exactly what they were asking for and exactly what part you're having an issue with. So do you have, can you show me a picture? Can you share a picture of it? Do you have a screenshot or anything like that?
I can try and screen share it. I just need to log on my laptop because I haven't signed on my computer.
No problem. I'm going to change the permissions so other people can share. Okay, it should allow you to share now. Has anybody else seen that problem or have a screenshot of that problem? Actually, it's just you and me, so never mind.
Can you see it?
Have you tried, are you on the computer that you're sharing screen with? Or are you using Zoom from another device?
I'm using Zoom. Yeah,
Okay, I have
I'm
it
here.
where you're supposed to be allowed to share it.
Loading really slowly. Oh, here we are.
There you go. Okay,
It's
to learn to calculate.
Okay.
Let me read real quick. It says to learn to calculate energy and momentum for relativistic particles and from the relativistic equations to find relations between a particle's energy and its momentum through its mass. The relativistic momentum P is gamma mv, of course, and E of the particle is mc squared times gamma. Yeah, that's the total energy. So I should add that as well. Okay, I say find the momentum P in a laboratory reference frame of a proton moving with a speed of 0.762 c. So yeah, you're supposed to answer that by, notice you got 938 MeV per c squared. If you multiply that by 0.762 c, which you obviously already did, then one of the c's will cancel out and you get that 1104 MeV per c. So I'm thinking you got that right, and I think that's what that check mark is. And for part B, it says find the total energy of this proton in the laboratory frame. So the total energy is just going to be gamma times the 938. So do you know how to calculate gamma?
Yes. So then the next part is just like, the next part would be using the actual formula that's on the screen, correct?
Yes. So what is the rest mass m of a particle traveling with speed with the speed of light in the laboratory frame? Actually, this is a little tricky of a question, but do you know what the mass would be?
The mass?
For part D. I didn't see part C, by the way.
Part C isn't shown because I didn't finish it yet.
Okay. So nothing travels at the speed of light unless it has a very specific mass. Do you recall what mass that would be?
No.
0.
Okay, got it.
And if you look at that, like you can look at Newton's second law. Newton's second law is basically gamma dp dt, or gamma m d by dt of mv. And you could put you probably should put the gamma, in fact, inside the derivative. But what you see is as the velocity increases, the gamma increases, which means and in fact goes to infinity as it approaches c. So the force required to bring something up to c is infinite unless the mass is 0.
Okay. Thank you.
No problem. Does that help?
Is it possible for me to email you like one other question after this? I have to go to lab after this immediately.
Yeah, no problem. Send me an email. I'll see if I can answer it.
Okay, thank you. Have a
All
nice
right,
night.
have a good one.